of faculty members, research scholars, and students. I think they deserve an appreciation for this endeavor. The objective of the webinar is to impart knowledge in the emerging areas like artificial intelligence, machine learning, blockchain, IoT, and their applications. This webinar will be held during 17th to 22nd May 2021. The lectures will be delivered by the experts from both academia and industry. As already mentioned by Gitosri, as speaker we will have Professor Amlan Chakrabarti, Director of A.K. Chaudhary School of Information Technology, University of Calcutta, Dr. Shubhomoy Chandar, Assistant Professor, NIT Durgapur, Dr. Suparna Vishwas, Associate Professor, Makaut, Mr. Sandipan Sarkar, IBM Kolkata, our own faculty, Dr. Vikramaditya Mondal, Associate Professor, BPPIMT, and our alumni member, Mr. Atanu Roy Chaudhary, founder of Capsule Lab. I'd like to thank all the speakers for accepting our invitation and joining us. Thanks to the department for organizing this webinar. Surely it will be beneficial for the participants, and I'm sure it will motivate some of the members to pursue research in these emerging domains. Also, it will help the students to meet up the recent need of the industry. Thanks to all the participants for joining us. I wish the program a grand success. Thank you.
Thank you, madam, for your enriching words. Now I would request our respected Emeritus Professor and former Dean Academics, Professor B.N. Chatterjee sir, to say a few words.
Good evening, everybody. Respected Professor Sudhapa Mukherjee, Professor Amlan Chakrabarti, Professor Shabnam, Head of the Department of IT, BPPIMT, other head of the department, and all the participants of this webinar of transformation technologies in recent days. I am sure all of you are going to get benefited by the talks given by eminent speakers, as mentioned by Gitosri Khan, as well as our principal, Sudhapa Mukherjee. We are very eager to hear, because today Professor Amlan Chakrabarti is going to speak about deep learning. Remember, these topics, those which are selected, machine learning, deep learning, artificial intelligence, these are the key technologies in the area of IT as well as computer science and in other areas for the new technologies which are being developed. And IoT has taken its shape in various applications. The present webinar has been very well designed to give a insight to some of these areas, and this is the right time. In fact, this institute, the Institute of Management Technology, is giving this type of webinar. Earlier it was seminar, workshop, etc. For last 4 or 5 years I have seen, and a large number of participants from many organizations, mostly education institutes, as well as other organizations, as well as the students of various institutes, faculty members, research scholars. They got tremendously benefited by these webinars, by the speech of the eminent speakers. So this is definitely going to help, because these are the technologies of the present day, recent days, as it has been mentioned. And the coming years, who knows what new technology is going to come. Maybe extension of this may be something else. And therefore, uh, this is going to give us a confidence. In fact, I know in the Institute of Management and Technology, most of the faculty members and most of our students have got knowledge about these topics which are mentioned and which will be given in future also. But even then, for the knowledge, there is no limit. Sky is the limit, and therefore, with the speech from the speeches of the eminent speaker, we are definitely going to be benefited. I don't think I should be between you and our eminent speaker, Professor Amlan Chakrabarti. So, without further, I wish this webinar all success. And I wish to thank the organizer for giving me an opportunity to speak a few words on this occasion. Thank you very much.
Thank you, sir, for your inspiring words. You always inspire us every time in this research field. Now, I would request our head of the department, Dr. Shabnam Sengupta, to say a few words in this inaugural session.
Thank you, Gitashri. Am I audible?
Yes, you
Am
are
I
audible. You are
audible?
audible. You are
Yes.
audible.
Yes.
Respected Principal, Professor Dr. Shutapa Mukherjee, our former Dean Academics and Advisor, Professor B.N. Chatterjee, Registrar Dr. Shubhashish Pradhan, other head of the departments, my dear colleagues, and all the participants, a very good evening to all of you. Today, we are going to start a webinar series on transformational technologies in recent trends, where distinguished speakers from academics, research, and industry will deliver their lectures on relevant topics of this era. Our today's speaker is Professor Amlan Chakrabarti of Calcutta University, and we are so thankful to him for delivering this lecture amidst his very busy schedule. Before we begin, we must appreciate that all of us are going through a very difficult time. Very recently, we have lost our former colleague, Sri Rajiv Bishwas. He was a very active and young person. His departure is a big loss for all of us. A few of our colleagues have lost their near ones in this battle. Before we start our session, can I request everyone to observe a minute's silence in the memory of Rajiv and everyone who is ending their journey because of this pandemic? Let us all pray that they rest in peace at their heavenly abode, and let us all pray that this phase gets over soon. Thank you. Thanks, everyone. Uh, on behalf of the Department of Information Technology of the Tibetan Institute of Management and Technology, as the head of the department, I welcome you all once again to this webinar series. May I now request Shudipta Roy to carry on further. Sudipta, please.
Yes. Thank you, ma'am. So, I'm just going to speak about our speaker, Professor Amlan Chakrabarti. He is a full professor in the Chaudhary School of Information Technology at the University of Calcutta. He is an MTech from University of Calcutta and did his doctoral research at Indian Statistical Institute, Kolkata. He was a postdoctoral fellow at the School of Engineering, Princeton University, USA during 2011 to 2012. He is the recipient of prestigious DST Boyscast Fellowship Award in Engineering Science 2011, Indian National Science Academy Visiting Faculty Fellowship in 2014, then JSPS Invitation Research Award 2016, Erasmus Mundus Leader Award from EU in 2017, and Hemit Visiting Professorship from University of Cambridge in 2018. Then Shiksha Ratna Award by Department of Higher Education Government of West Bengal in 2018. He has also served in various capacities in various higher education organizations, both at national and international levels. He has received multiple project grants in the areas of security, in cyber physical systems, embedded system design, VLSI design, quantum computing, computer vision, and data science from various national and international agencies like DST, DRDO, UGC, BAE, then Ministry of Social Empowerment, WBDST, then Tata Consultancy Services, Intel India, etc. He has published around 150 research papers in referred journals and conferences. He is a senior member of IEEE and ACM, distinguished visitor of IEEE Computer Society, distinguished speaker of ACM, secretary of IEEE CEDA India chapter, then vice president of Data Science Society and life member of CSI India. His area of research interests are quantum computing, reconfigurable computing, embedded system design, VLSI design, computer vision, and machine learning. Today, we are really privileged to have an opportunity to listen to him. Now, I would like to request Professor Chakraborty to deliver his lecture. Sir, please.
Yeah, thank you, Professor Sudipta, and thanks to the college, the BP Poddar Institute of Management and Technology. This is a very known institute for me, and also I thank the Department of Information Technology, Professor Shabnam Sengupta, Dr. Gitoshri Khan, and this is a fantastic endeavor from the department and from the institute, because as we know that all of us are very depressed at the present scenario. Many of our colleagues, many of our friends and relatives are not in a very good state. But somehow we have to be busy with the path of the knowledge. That's the most way we can keep busy. We all of us are happy when we study something new or when we try to learn something new. And so this type of efforts from the academic institutes are really great, and I am very happy to be a part of this. So my today's lecture will be on deep learning, and I will try to focus on some of the recent advancements of deep learning in the area of computer vision. And so in this lecture, I will not touch many of the basics, which I normally touch in many of the faculty development program, but I thought that this particular workshop is just to enlighten some of the emerging areas so that the faculty members, the young researchers, the students can just take the path, what's happening new in this domain, and they feel interested and they try to catch up from there. So with this, let me start my presentation.
Yes, sir. Yes, sir.
Yeah.
Sure.
Yeah. So I hope my presentation is visible to all of you, right?
Yes, sir. It's clearly visible.
So, this is the title of my lecture today, which is Spatial-Temporal Fusion Using Deep Networks. And I also, when Professor Shengupta called me and requested me that whether I will be interested to deliver a lecture on some of the emerging topic, right? I just thought that I think this will be the topic which is very emerging, because in our lab, we have a data science lab. Some of you might know this, in our department of A.K. Chaudhary School of Information Technology, University of Calcutta. Though we have many research labs in our department, at least 4 research labs in our department, but this is one of the research lab which has just come across for the last 3+ years, due to the effort of not only me but many of the faculty members of my department, and also some of the research scholars, who graduated from our department, but they are now pretty well known in this domain of data science. They are also contributing a lot. So this is a new direction which my research group has taken for the last 6 to 8 months, and we have PhD students and interns who have just started working in the field of spatio-temporal fusion. And I thought that the way I have tried to push this idea to my research scholars, why not I try the same thing to the faculty members, the researchers, and the students here. That's why I chose this topic, and I hope that this will be an interesting topic to all of you. Might be you might find that some of the concepts you need to go to fundamentals, which I don't have the scope in this particular lecture due to a limitation of time. But obviously, if anybody wants to connect with me after my talk, I will be happy to connect with him or her on this. So, we know that deep learning, the term deep learning, is something that by which we try to extract the features or the abstractions, which are in a much higher level. And that is very difficult for the normal neural network to achieve, because the normal neural network, we don't generate this hierarchy of feature spaces. So what deep learning does, deep learning tries to generate in a sequence the feature spaces, which starts from a very primitive feature description or the low-level features, and gradually it goes into a series of layers or a number of layers, right? And that generates the concept of deep network. And through that particular network, which has number of layers, it generates a learning paradigm, or it creates a learning paradigm of the features, of the input, which helps us to classify or to know about the input image or input data. Actually, I'm telling image because the initial use cases of deep learning in the context of convolutional neural network started with image. So this deep learning or deep network helps us to abstract the very high level features slowly and steadily through multiple stages of the network, and so that we can extract all the important as well as the features which are very deeply seated in the information space, and which helps us to resolve the differences, or to categorize the objects which can be very similar but still different, right? And those challenging use cases can be very well handled by the deep neural networks, and the process is called deep learning. So as I show in this particular process, in the workflow, so what I try to identify that whether this particular image represents an indoor or an outdoor information. Okay, I have to just try to classify this image. So the way it goes on is that it tries to work with the low-level features, which can be predominantly the simple edges, and then the edge informations which are spatially adjacent, okay, forms the next level of features, which may be some object informations, and the objects which are again spatially adjacent, okay, will form, okay, a sort of abstraction of the environment, okay, which describes the image, and that helps the classifier to give a very decisive output, okay, of classification. Now, when I tell this, you have to understand that I have used a term called spatial, and that is very important in terms of the conventional deep learning or the conventional convolution network, which actually works in a spatially distributed data. Image itself is a spatially distributed data, but the way it works, the convolution kernels, it tries to work on spatial patches with a guess. Okay, this is very important. Okay, with a guess that the feature which I try to extract is spatially localized, right? This is very important to understand that what is the difference between traditional neural network and traditional convolution neural network, because both are neural network. Only the term, the way it differs is the convolution, and this convolution actually spatially localizes the features and tries to generate the feature space which are determined through the spatial operations of the filters. So let's go on this. So this is the way it tries to generate the okay, at the first level it can generate the edge orientations or edges, and then it can go to the connected edges, then it can go to some of the texture informations, okay, apart from the edges, and then it goes on and try to detect the objects and try to go to the higher level of higher level of object, okay, that means trying to find the correlation between a set of objects and trying to describe the particular scene, right? And that's what is a deep learning. Now, if we go into the very fundamental of this understanding, right, how it works, I think this has been for anyone who has gone to the deep learning course or the text book of deep learning might have gone through all this. But just to repeat on this particular idea, which is very important, but this is a particular patchy operation. The convolution operation in the other way is also called a patchy operation, because it actually works on a sort of the input image, which is this, right, is actually converted or is actually segregated as patches, right? And these patches are similar to the size of the kernels. And then what happens, the most easiest way of describing a neural network operation is something like weight multiplied by input, right? If you all can remember, Okay, it is something, a summation over I. Okay, actually I missed the other laptop, so I'm not connecting with actually with the writing pad, but let's try to do it by the pen here. Okay, so xi star wi. So xi star wi is the preliminary, is the over I, is the fundamental of neural network, and this is w0 is the bias, which actually, and this actually is operated by a function f, right? Which may be a nonlinear function. Sorry, this is a function f, and then it produces something called y. Okay, so this is actually a okay. Don't take it at a minus or something. Just cancel it. This is a function f. Okay, this is a function f. I hope you will understand this. So this x multiplied by y, by wi, xi are the inputs. Okay, these are the inputs, and these are the weights. And these weights, in the case of CNN, comes from the kernel values. Okay, so we have w0, w1, w2, w3, w4, w5, w6. So like that, if we have the kernel here, right? If we define a kernel function, which may be something like this. Okay, this is a kernel function. If we try to say, and this kernel function may be a 3x3 kernel function, which has w1 to w9 weights. So it works with the 9 elements of my input and tries to multiply this with the kernel weights. And each of these operations is a convolution operation, right? And so the convolution operation, which is a weight multiplied by input, instead of the standard neural network, which works on the entire input, right? If you remember the standard neural network, it works on the entire input from x0 or x1 rather. X0 we can take the bias, x1 to xn. Okay, which works on the single input, the input as a one shot in the standard neural network. In the convolution neural network, what happens is that you try to make a piecewise operation, the patchy operation on this two-dimensional input, and that's the convolution. So convolution outcome generates these values. Now you see that instead of one convolution outcome, you have several convolution outcomes. What does this mean? This means that, hey, this convolution plane is generated by one particular kernel. Okay, this convolution plane is generated by one kernel, right? And similarly, there can be a number of kernels. Okay, one kernel is detecting maybe the average value. One kernel is detecting the diagonal value. One kernel is detecting the cross diagonal value, right? One kernel is detecting some sort of connectivity between the pixel information. So there may be, so each of these kernels, right? Each of these kernels, what generates the convolution outcome are your features, right? Are your defined, actually work for a particular feature. So if we have the input and if we have the stage one, so in the stage one of convolution, what we have the feature maps. What is the feature map? Each of these kernels generates a feature, right? And how each of these patches, okay, responds to that feature that is being recorded at any layer. So whatever is the previous layer data, on that I apply the convolution of that particular layer, right? And then I generate the feature values, okay, of that particular layer. And then on those feature values, again, the next layer works on. Now, apart from the convolution operations, there are two other operations, right? One is called the activation operation, and another one is called the pooling operation. So in the case of pooling operation, what we try to do, we try to reduce this particular dimension of the feature, okay, by some sampling. Okay, we try to take a 4:1 okay, type of sample. So four adjacent adjacent values represented by one value, and that can be a max or that can be an average of that. And then what I can also do, I can try to do an activation function or a nonlinear function like a ReLU, okay, which actually tries to normalize that. Normally, it can be simple like that. That if it is a negative value, okay, it just responds 0, and if it's a positive value, it responds to the value what is generated. So in this way, we try to do a dimensional reduction. So which means that the spatial feature gets compressed. The feature space gets more compressed and compressed in the spatial domain, right? Once we go from convolution layer 1 to layer 2 and layer 3 to layer 4. And also what I try to abstract through this particular activation function is that I try to get hold of those values which are contributing as features. The values which are negative, right? Or in some cases, we can use an activation function which are for a small positive value also, it pushes to 0. And if the value is above a threshold, it pushes to 1. Okay. So we try to take the values which are contributing, and we are also trying to squeeze the spatial dimension in each of the iterations, and that actually gives a very a very high level abstraction, okay, of the input information, right? And this is the way the pooling and activation we try to define the convolution neural network. And at last, I have this is very important again. So what we had is in a normal neural network. In a normal neural network, we had all the inputs, and then gets pushed into a network. At the last layer, we have something called flattened network. And what happens in the flattened network is that whatever features you have generated from the previous convolution layer defines a one layer input. And that one layer input is fed to a neural network, and that works as a same as that of any neural network does. Okay, so this is what is actually convolution. So we can actually make the two disjoint operations. One is called the convolution operation, which generates the feature space, right? And then the convolution, then the standard neural classifier, which classifies as a normal neural classifier works, right? So the contribution of convolution is just to generate the feature space which can give you more clarity, okay, at the classification, and which also carries the features, okay, on a spatial in a spatial coherence. Okay, so if you understand this, then it's very simple for us to do. So these are what is the filter operation on the image, and this you can just, so this is the convolution operation, as I told. So it moves the kernel, the filter kernel, okay, moves across that, and this filter kernel actually tries to capture a particular property, which is something like a okay, it's a difference of the center pixel, okay, from the 4 immediate neighbors. If we just try to do it mathematically in the discrete domain, you will try to find that this kernel tries to find a difference of the center pixel with all the adjacent, and that difference defines that whether it has a gradient, whether it is a sharp gradient from its neighbor. So that can be an edge, very simple an edge, right? So this is the way how we can do it, and see you have generated all the edges here. Okay, this particular kernel generated all the edges, and that's the way it works. This is a very simple. Okay, the concept was pretty early, 1960s. Actually, neural network was around 1950s, right? And some sort of assumption of the neurophysiological experiment done by Hubel and Wiesel, 1962, which all originated this particular type of networks. And this is actually the network which is very, very closely resembles, okay, how our brain network works, or how our biological network works, because in our brain we have different regions, right? And what's the purpose of each of the regions? You know that purpose of each of the region is abstracting different type of senses from the input. So it's very similar to the different types of convolution kernels which generates the feature space, okay, which extract the features. Okay, so having known this, I'm just quickly moving on this. I'm not getting into details of this. I've already told that it is same as the neural network, weight multiplied by the inputs. Only the input is the patch in your image, and the weights are your convolution kernel. That's all. You try, if you can work on this, you can generate the convolution outcome, and it's pretty simple. Okay. So this is what is the layer-wise view. That means it goes on layer-wise, and it tries to also squeeze the spatial dimension okay, moving in this way. Again, this is a very standard way we see a network, right? We see a standard network, and this is the way how these are all the kernels, right? The filter convolution kernels. You can have a different networks are there. I think there are very. If we just try to do an initial search at Google on the convolution network, you can at least find very quickly at least 10 networks, at least. Okay. So I'm not getting into the details of the networks. I'm trying to tell that, hey, what is a convolution network in general, right? Right, and this is the convolution network in general, and then what it comes out is, as I told, that it is the output vector what it tries to generate a particular flattened network. Okay, after we finish the convolution, and that flattened network gets into a fully connected neural network and tries to and can work as a that means, and we can design the classifier. The most common classifier is the softmax classifier in this particular part of the network. So the classifier classifies that whether this is a what type of room it is, right? Provided we have already trained this network with a number of images for each of these classes, so that it can record the score, right? The score of each of these classes, and then for an unknown input, it can evaluate the score, and based on that score, you can push it into it can predict its class value. So that's the way how the convolution neural network works. Now let's get into the understanding the domain, right? So our domain here is spatio-temporal fusion. So when we tell spatio-temporal, it actually points not to the image, but to something which also has a temporal dimension. So an image information has only a spatial dimension, right? An image is defined by a function called IXY. The XY are the coordinate position or a coordinate value of a pixel. What is a pixel? Pixel is an unit information of an image. The particular image is defined by a number of pixel information, right? And so an image is a function of IXY. What it means that if you give me the XY value, okay, so if I have an image, and if I query the image with a particular value of X and a particular value of Y, the image data will respond, right, and will return me the particular intensity value for the pixel whose coordinates are X and Y, right? And that's pretty simple. When we try to use the temporal dimension, then what happens is that we are going to videos, right? Because videos not only has the spatial variation, it can have a spatial variation, because video is nothing but as you see here, right? As you see here, the video is nothing but a temporal spread of image frames, and each image frame is identified by IXY. So actually, this entire information is identified now by 3 parameters. One is X, Y, and T, because the same XY pixel value can change with the time T, right? And that's why it's a IXYT. Now, if we look into the role of video, the role of video in the present scenario of automation, or in the present scenario of smart world, is enormous. right? I have only shown some of the some of the some of the things what I just got from Google. Okay, some of the very attractive examples, right? You can find many more of this, right? So robotic vision, we know that robotic vision is coming to a great extent, and especially in this pandemic scenario where we don't have the manual intervention of every work in many of the offices, okay, as well as in industrial sector, right? It's already started that a lot of robotics activities are going on, and the robot understand the environment by analyzing the one of the way of understanding the environment is analyzing the objects, okay, what it captures in the real time, okay, and real time what you capture is the number of frames, and that's the video. So robotic understanding is one of the okay, robotic vision, okay, one of the aspects of robotic vision is video analysis and understanding the video, right? Where a lot of autonomous operations like autonomous vehicle, autonomous car, right? They are the understanding the scene, understanding the road environment, understanding the pedestrians, understanding the obstacles in the road, right? It's pretty heavily dependent on this understanding and analyzing the video data. Sports analytics, which is of a very okay, one of the very important activities what we do in our department. Uh, we have published a couple of papers in this domain very recently with one of the senior collaborators from Indian Statistical Institute, and so this is also one of the where the video analytics we can actually try to know the information, what is the activity going on in the particular where a lot of human and non-human are involved, right? You have to know the activities, and this is an example where you have a sports or a game is going on, and you try to find the activities of the players. In the medical scenario, which is again one of the very impactful domain, not only at the present pandemic scenario, but it will be always be there. Whatever you do in technology for medical, we are doing it for the last 7-8 years. Okay, a couple of my students have finished their thesis, and some of they are on the process. So the medical contribution to the medical domain in terms of technology and in terms of analyzing the videos, because a lot of medical imaging now captures video to understand the exact movement or the exact activities of an organ or the human body as a whole. Okay, so this is some of the salient examples, and you can find many more like this. Now I'm not going to this why motion is useful, but what's more important is that what is motion? So motion is identified by a vector information, and the vector is basically from that means if I am at frame, if I am viewing frame t, which is captured at time t, right? I have an image frame which is captured at time t minus 1, and I also have a frame, okay, which is captured at time t plus 1. So we try to move from t minus 1 to t and t to t plus 1, and we try to find the how the pixel information has done a spatial shift, right? And the spatial shift between the frames. Now the spatial shift is not in a particular frame; it is between the frames, right? And so there is a vector, right, which can be estimated by comparing two frames. Now the dimension of the vectors will be large, where a particular intensity information, okay, in frame t minus 1 has spatially shifted at least a considerable amount, so that I can detect I can find the finite dimension of the displacement as a vector, right? And similarly, if I try to do this for all the objects and for all the frames in my image, what I generate a set of motion vectors. Okay, now Now, this particular generation of motion vectors is called a flow. What is a flow? Flow means that something is changing and there is a direction. So there is a change in the optical information, in the intensity pattern, okay, across the frames which are in a given video, and it defines a direction, and that's why it's called a flow. Now there can be some issues which we are not considering in this particular lecture, right? There are a lot of, so you can tell me that hey, I can change the intensity of my source and my, okay, and I have the same object captured at different intensity, right? That will obviously create an intensity change in my consecutive frames, but that's not actually the real positional change of the objects in the consecutive frames, right? Yeah, that is there. That can be an issue, but we're not considering that. Okay, we're trying to consider the illumination station is constant. Okay, if your illumination varies with time, then you will automatically have an intensity fluctuations across the frame, which might not be due to the change in the position of the objects in the consecutive frames, but due to this intensity change. Because you know the function Ixy is a product of illumination and reflectance. Okay, so if your illumination or reflectance, okay, that means if your illumination varies, right, your with time, your Ixy will also function of time, but that we're not considering this. So if we look into this particular diagram, this is a vector filled information, which is a spatio-temporal information, because you have the spatial objects which are changing their position in time. So the spatial changes, right? The spatial changes are being captured in time references, distinct time references, and that generates the spatio-temporal information. Okay, and this is in a more better way. Okay, so what I show here, as I just told you now, that hey, this is this is my Ixyt minus 1, which are these points. Okay, let me try to. So these are my points, which are actually Ixyt minus 1, right? And these are my points, which are Ixyt, which means the next frame, immediate frame in my video after this t minus 1 frame. And if I try to superimpose this on this, and then I try to find the vector displacement, okay, between these two frames for each of the points, what I will generate is the vectors this, okay, and these are what are the motion vectors, okay, and this is called a motion field also, right? And based on estimation of this particular optical flow, there are also other type of information we can generate. We can generate the whether we are capturing the information of a static object or a moving object. And in some cases, if we have some reference data, we can also capture what speed the object is moving. But actually, that means those are not the days of deep learning, and might not be machine learning in that way. We had soft computing in 2005 or 2004 rather. Okay, when I was a faculty in one of the engineering colleges, okay, in Calcutta, right, I got the DRDO project, okay, which actually was based on this particular the technique what we developed, okay, for the project was under the Vehicle Research Development Lab, VRDE Lab, Ahmednagar, Pune, okay, yeah, Maharashtra, better. And there our project, our activity was to detect the dynamic obstacles, okay, for an unmanned ground vehicle project, UGV project, right? And from okay, so optical flow and motion estimation using optical flow, and the features of optical flow is not which is only very new. It existed, I think, at least for the last 20 plus years. So key assumptions, as I told you, that obviously the things becomes difficult if we have a illumination or the brightness changes with time. Okay, that will have some other effects. Small motion, obviously we cannot. Okay, if the motion is very large, then some objects may be out of the frame. In the next frame, the object will not be there, right? And that will be difficult to how to generate this particular vector, right? And spatial coherence. So if I am defining a particular vector, okay, that means you have to remember that these are all pixel informations. The way I can visualize the image or I can process the image is only based on the pixel information. Now, also you have to agree that the pixel information of an object, of a particular object, the pixels of a particular object, which may be a surface, are pretty close to one another, right? And when I tell that, okay, that the object moves, it moves, the entire surface of the object moves. It will be very difficult, right, if the object is non-rigid. Right? If the object is non-rigid, then the surface of the object doesn't move in the same way, right? And that's again a difficult problem when we have non-rigid objects. But the preliminary assumptions, the basic assumptions of the optical flow are these three. Okay. So, any questions before I move into the spatio-temporal fusion techniques? These are the, I think these are the, okay, I have ended the preliminaries of the convolution. I have just tried to set the baseline of this lecture. Okay. So if anyone have any queries or questions, they can ask me. I can just take a couple of questions.
So, any
Sir.
question from the participants?
Yes,
And
yes, Gitoshi ma'am. Sir, there is a question from Kaushik Shingho Roy that how you can measure percent level of participants?
Percent level of
Participants.
participants. What context the question is there? That is, what's the context of participants here?
Okay, sir.
Can
Sir,
you just?
I think Shanton, is this question from YouTube or from the GMIT?
Yeah, ma'am. This question is from YouTube.
Okay. Any further?
Yeah. So what I have discussed until now is just a basic background, which actually covers up the technique of the deep learning or deep networks, and obviously the domain information of the image and video. That's all. I didn't cover anything beyond that. Okay. If any questions are, that was, I will get back to this. Okay, that was at the end of my talk. If there is a question on the how we can estimate a video and the number of persons in a video, I think that's the question. But
yes, sir.
Okay, but
yes,
the point, but up to present time, I didn't gone into that particular context. So if there any question exists in understanding what I have discussed until now, that means you can ask one or two questions, right? Otherwise, I can just move ahead.
Okay, sir. I think right now no more questions are there.
Perfect.
Yes, sir. At last we will see. Okay. Okay, sir.
Fine.
Okay.
So let me move to the. Okay. So so the next thing is that as I have proposed the video, so you need to, that means as you need to prepare the models in the deep network domain, that means you need to work that what are the type of data sets, annotated data sets we have. I have given us a few lists. There are more than this. Okay. And you can look into the data sets there. They are annotated. They are labeled data sets, so you can use them as your training data. Okay. Recently, I've also got to know about a tool. I think that means if anyone is interested, that means I can forward the tool or the link. So One of my US collaborators have recently developed a tool where you can actually, okay, automatically annotate your own videos, right? They have a large samples of repository videos, and then when you supply your video, they will try to classify your video. So so you don't have to do the label on your own. You can use the tool for labeling, right? And then if you can see that, okay, there are some errors, you can correct the errors individually, but that will be quite a small proportion, and you save a lot of time in annotating your videos. Okay, so let's go into the core topic of today's discussion. Okay, so this is our focus of this lecture, after I covered the preliminaries, is how to do the convolution, or how to operate deep networks on video, because video itself means spatio-temporal information, right? And these are very very recent works. When I tell that the first paper comes out in 2013, right, you need to understand that, yeah, this is really a domain where you still can work upon. Okay, because normally, okay, if you have a domain which is existing for the less than 10 years, right, I think there are a lot of work you can do still, right? Okay, so 2013, I don't know, that means, I think, if you have any other reference, but what I found in the reference is that the first phenomenon work, or actually the 3D convolution neural network paper, okay, was being published in the IEEE PAMI in 2013, right? And this is what is 3D convolution neural network is, right? So let's try to understand what they are. So this is, so the first is the simple 2D convolution layer. Okay, what it does, you can just try to tell this. What is this Vijxy? So Vijxy is the jth feature map of ith layer, right? So if we look into the convolution operation, as I told, there are multiple layers, and in each layer there are multiple kernels. So the kernels are your feature map, and ith is your layer. So a particular value, okay, a particular neuron value, okay, for the kernel, for the jth kernel in the ith layer is Vijxy. Why xy? Because it's a two-dimensional. It's on the single image, right? And there will be a bias, and this gets into this tanh, a nonlinear function, and we try to generate that. Hey, what I put in Vijxy? So we generate Vijxy by a convolution function which is defined by this, okay, right? And m, what is this m here, right? M is basically the number of channels. Basically, if you have an RGB, you have to do 3 channels m, okay? Now, when we try to do a 3D convolution, what happens is that instead of one image frame which was here, I take a sequence of image frame, okay? So this is my input now. It may be 5, it may be 10, it may be 15, okay? Obviously, it depends on how complex you want to make your 3D convolution network, right? So what I have one more, okay, one more particular operation here, which is defined by R, okay, Z plus R. So R is the spatial spread. R is the spatial spread. So what it tries to do, it also generates a multi-dimensional VIG. Okay, here VIG was 2-dimensional. Here VIG is also multi-dimensional. You can have a 3-dimensional, okay, VIG. And And each of this VIG XYZ depends on a spatial distribution defined by XY, right? Which x extends from 0 to p minus 1, okay, 0 to p minus 1, right? And y extends from 0 to q minus 1, and r extends from 0 to r minus 1. So these are your spatial spread and your temporal spread, right? Based on this, you generate your VIJXYZ. Now in this, obviously, if you see the network size, okay, the number of parameters you have to handle, right, increases to a lot. But this is what is a 3D convolution kernel, which can be also be signified like this. So your data, right? Your data consists of a time axis, which is this, okay, and a space axis, this by this, okay. So this is your data, and this is your kernel. So your kernel tries to work with. So this is your entire dimension of space, okay, and this is your entire dimension of time. So now your kernel works patchy. Try to understand. Kernel works on the patch. So kernel works on a patch of XY, which is defined by the spread of actually P and Q. So this is the spread in the spatial dimension, and this is the spread in the temporal dimension, right? So your kernel will also have 3 dimensions. And then what will happen? Then as it works out, an entire 3x3 working on a 3x3 weight function working on a 3x3 image after convolution generates one particular value. Similarly, this entire convolution operation generates one cube, which is a particular value, okay, in a particular for a particular compressed sequence of frame, right? A particular feature, okay, a particular temporal feature, okay, and spatial features, okay, in X and Y. So it also generates a particular, a cube of one dimension, right, in each of the axes. So it generated the feature space, right? And then this convolution operates on each of this in the entire voxel, right, and generates the reduced feature space in the 3 dimension, where again these are the spatial feature spread, and this is the temporal feature spread. Okay, and this you try to go on doing this, and if you try to expand it, this will come to like this, and you can go on doing this into multiple layers, and that is what is called a 3D convolution. Okay, and there may be different types of kernel operations you can do. These channels, see, there are channels. So the channels may be detecting the gradient, detecting the grayscale information. So grayscale information is basically the average information, average intensity function. Gradient across X, gradient across Y, optical flow across X, optical flow across Y. So this may be your preliminary channels. Okay, what you try to convolution filters, what you try to generate, try to act upon on this on this particular image, on this particular video sequence, right? And this that's all what is the 3D convolution network. Okay. So how much time I have still now?
Sir, you can continue. No issue. You can
Okay,
continue.
okay, sure. So considering that the 3D convolution network is which was proposed in 2013, okay, is becoming a very extensive activity, right? In terms of training. Actually, the cost is in the training. if you have multiple parameters and you have okay, you have to work with okay, weight vector, okay, which is pretty complex, right? You need to do a lot of hard work in the training. Okay, so can we do something better? So I think everyone, that means many of you know this Karpathy. Okay, he's one of the okay, very predominant contributor in the domain of computer vision and deep networks. So their group proposed another model, which is called a two-scale convolution model, right? And this is very interesting. Okay, they developed two, that is, instead of doing a sort of sort of entire image volume and try to generate it on one full go, right? They define two streams. Okay, and these streams are defined as fovea and context. What are these? So fovea is something which is in our eye. It is something like a central sensor. So our fovea is the central part of the eye, which actually captures the information which is centrally in a visual scene. And context is the overall information. So what this particular technique does or proposes is something like that. You have suppose you have a 178 plus 178 pixels, right? So now it decomposed it into two streams. Stream one, fovea stream. What it does, it takes 89 cross 89 pixels from the center of the image. Okay, again I repeat, from the whole image it tries to take the 89 cross 89 pixels from the center, and then it downsamples the original image 178 cross 178 pixels. Means each 2 pixel is represented by its average intensity and made 1 pixel in the downsampled image. This is a very common technique we do in downsampling. Okay, so 2 pixels are converted to 1 pixel by their max or average, whatever policy you choose. Okay, and that downsampled image will also be 89 cross 89 pixels. And then you actually use the standard CNN, okay, for both the streams, right? And somehow you generate a classification score from both the stream, right? And then the classification score, you try to take a mean of that or try to take a max of that. There are certain techniques which I'm not detailing here, but the most important part is that you can, okay, the technique of converting, okay, and a video frame into 2 channels, right? And that was the okay, or 2 scales. Okay, one is magnified, the fovea part, and another one is the compressed, which is the context part, right? And so it is something, the localized information at the central, which carries the maximum perception of the image, as well as it doesn't lose as much of the context also, right? And tries to correlate the two information. Okay, try to take the features from 2 information and then try to classify the particular video information, right? And that was a predominant application which was developed by this group in 2014. Now this is very important to understand before we go to the next schemes, that okay, if you look at this is also proposed by this paper by this paper of okay, Karpathy, that what are the ways I can take this particular, so which frames I will take. This is very important. Okay, and how I will fuse. Okay, so there are various options. Okay, the options like single frame fusion, lead fusion, early fusion, slow fusion. Okay, So you can, so you have an image, okay, so you have a video sequence. Normally this video sequence, okay, can be converted into some keyframes where the changes are pretty high. There are some standard techniques out there, right, by which you can convert a video sequence to keyframes. So what you can do, you can choose one frame from your video, right, and you can do this job. Okay, you can do this job. Okay, whatever I have done here. Okay. Okay, you can do two end frames of the sequence, and you can do the fusion. Okay, you can do some consecutive frames and leave some of the frames. You can do that. Okay. The most the effective one, which is being reported by many literature, is the slow fusion. In the slow fusion, what is done? It is a sequence of frames which are being taken, right, and they are fused. They are fused in an hierarchical way. So they take the frames in a three neighbor way, right, and they try to do this fusion, and then the next layer of fusion, right, and then the next layer of fusion. So this is also, but this is a slow fusion because it will take a long amount of time to evaluate your outcome. But slow fusion is okay. It is being reported by most of the literatures that the slow fusion is very effective. Okay. But it is also being reported that if you can take an average, or if you can take a sort of model like a multiple classifier in a multiple classifier, and you take a voting of that, or you take a majority of that, I think that can also work. But again, that depends on your application requirement and the resources what you have. But this is one of the understanding you need to have when you try to use the images from a video and try to fuse them in some way. What are the strategies you can have? This is also a very phenomenal paper, which is also published in the conference of NIPS, and this is also a very highly cited paper because it actually coined is a two-stream convolution networks. Now the difference between this is again a landmark in the domain of spatial-temporal fusion, because this particular work first proposed the use of temporal features. Okay, remember, temporal features means the features which are generated by the optical flow. So what it did, it actually taken a stack of frames, okay, in a video, and from it took a single frame for the spatial information, for extracting the spatial information. How you choose the single frame? You can take the tth frame as a single frame, and you can go from t plus p and t minus p, and you can take the video. So the central frame of a particular sequence of video you can take as a single frame, and you can pass it to the spatial feature, and then you generate the optical flow parameters. Now there are two types of optical flow parameters. One is called optical stacking, and one is called trajectory stacking. Okay, one is actually based on how your UV moves. So which is more conventional. Okay, so you have the UV pixel P1, right, and how that means where the pixel moves in the next frame and next frame and next frame like this. Okay, right? In the case of trajectory stacking, you try to find a particular path in the particular image sequence, right? And try to find that whether this particular trajectory is being followed by the consecutive by the pixel in the consecutive frames. So there are two ways of trying to understand, but whatever is the way you generate the optical the optical the motion vectors, right? Or the optical features, the optical flow features. Okay, this particular network tells that, hey, you try to extract the features from the optical flow data, which is called the temporal stream convolution network, and you take the kernels on the spatial kernels on the single frame, and then you try to fuse that, and then you try to again take a score that, hey, okay, this tells there is a person, so the spatial convolution net can tell that, hey, this is a person having a bow, and then the temporal convolution net can tell that the bow is moving up and down. Okay, and then fusing this, you can tell that a person is moving the bow. Okay, and this is the way you can annotate the video, or you can classify the video. Okay, this is a very landmark research what was being done in 2014. Now, this is a little bit modification of the two stream. Okay, here I'm not getting into details of this again, but here the issue is that you don't fuse it at the last. Okay, it is just an extension of this two-stream convolution network fusion. It is just an extension of this. So what this group modified the 2014 work to 2016 is that instead of doing a convolution, doing a fusion at the last, okay, they do the fusion at various ways. Okay, and when they are doing this fusion, okay, they are actually doing also the 3D pooling, because here the pooling are basically normally done in the very normal way, right? Whereas here the pooling is basically done taking both the spatial and temporal information. So it is generating, okay, initially it is generating the spatial and temporal information up to some level, but then it is fusing, and then it is extending the convolution on the entire stack, which takes into consideration both the spatial information and the temporal information. And you see the different types of fusion stacks they have defined. So if we look into the previous diagram, the previous model, and here in the previous model, you would have done the spatial and the temporal only at the last stage. Here you have different options. See what you do. The combination one, they have done a convolution operation on the temporal here, convolution operation spatial here, and then they fused it here, and then they again run the 3D convolution and 3D pooling combination, okay, on the fused information, right? And here it's a different type of approach. It's sort of a hybrid approach. So one is straight going on spatial, and another one is a hybrid of spatial and temporal, and then they're fusing this with spatial. So this is also a very interesting approach in the fusion of the spatial temporal fields. Okay, this is again a very important aspect of this. Okay, a very important landmark in the spatial temporal fusion. But it was a CVPR work on in 2017. So this is a different types of representation, which is called a TLE. So temporal linear encoding. So what does it mean? It means that it takes the spatial frames. It takes the spatial frames which are here. Sorry. Right, and these are the temporal frames. Right, and it generates. It takes each frame individually and runs multiple convolution networks, okay, concurrently for each of the frames here, and similarly multiple concurrent networks for each of the optical frames here. And then all this, they concatenate and generate one representation. So this is very important. So they actually concatenate all the representations. Okay, they concatenate all the representations. So S1, S2, and Sk are the representations of all the k all the k number of frames, right? So they do a similar spatial concatenation, okay, of the feature space coming from all these spatial frames, and they do a concatenation of the optical space, and they again do a concatenation of the optical feature space, and they represent it to okay, and there is a special encoding phenomenon. Okay, now they fuse both of them, right, and that's the way they try to work upon, and they have shown that okay, this is also giving the better results compared to the previous multi-channel based spatio-temporal fusion. Okay, these are the things. And so if we try to summarize of all these things, what are the ways, though I have told that is action classification from video, but it's basically analyzing the video or extracting the information of the video. So there are different ways to do that. Okay, the preliminary way is the 3D convolution network, okay, which is actually works over all the frames and does a 3D convolution net. Second is the convolution net parallelly working on the spatial, okay, from one image, and the convolution network which is working on the optical flow parameters, optical flow primary features generated from multiple frames. Right? You need to understand that what I supply in the network is a feature, is a set of features, right? So the optical features are supplied, and then the convolution network, okay, generates a higher level of abstraction, and then the features are fused. Either we put the classifier here and classifier here, and then we take a score of the two classifier, or we can fuse that and we can take the classifier after that. Okay. The other one is that, hey, I take the spatial 3D convolution network, and I take the optical flow convolution network, and I then fuse it. Last but not the least, okay, which I think that I don't know, I have time to discuss further on that, but there are also techniques to add an LSTM network, LSTM models. What's an LSTM model? LSTM model is a memory model, okay, which actually understands the sequences and tries to understand the features of the sequences, okay, through some memory, to some memory functions, right? And that memory functions tries to propagate the features which were far prior to a particular frame, okay, and it can concatenate, or it can connect that feature, and then it can use it to classify, or use it to generate the outcome. So so there are usage by which that it's not only convolution network, but you can also use an LSTM, and then the two LSTM models will connect it to each other in a specific direction, maybe from the okay, in the temporal domain, right? And so what it is done is that means for each images you are generating a convolution network, and you are trying to find the features, how the features are varying with time using the LSTM, because LSTM tracks the sequence. So you are trying to find out how the features varies with the time using the LSTM part, and then you can define the action. Okay, so these are in a very summarized way. What I tried to tell you is that these are the ways how we you can do the spatio-temporal fusion, and you can analyze the videos for multiple activities. Okay, to help you to understand the environment, to understand the human action, to understand the scenarios, the analytics. Okay, and these models are very evolving models. Okay, I think I have only covered some of the very well-known models, but there are many others. At least you can find 10 more models which are there in the published literatures. Okay, to handle this spatio-temporal fusion. Okay, so I had some more things here, but I think it will stretch further than an hour, and I will just skip this. I will not go on this further. So I will go to the future. So there are some okay, it's not future. People have actually started working on that. If you look into the latest CVPR activity, CVPR publications in 2018, we have very two good papers where they are not only trying to tell about the video, but it's also trying to tell the pose of the human, and that's actually the work what we are trying to do at present in one of our research activities. So it's not that okay, it's a cricket match. It's not only that, right? In a video you can tell that here this is a cricket match, or here this is a ball is being okay, there is a player and a ball. It's not like that. You are also telling that okay, now the batsman is hitting. Okay, so you are also telling the pose of the human, right? And that's very very important. So you try to use an attention layer. Okay, an attention layer which tries to which is a type of evaluation of a score, okay, of some of the possible possible events in a given sequence, right? And through the attention layer, you try to specify a particular activity, right? And then try to trace the activity in your video. This is one of the work which is now being very well done. And you know that there are a lot of activities in the present pandemic scenario where people are taking the help of their trainer online. So you have an online trainer, right? And you are either doing some physical exercise, or you are trying to perform some sports, right? And your trainer is on the other side, right? And okay, and this type of techniques can analyze your video and can tell that how accurate your pose was, how accurate your style of hitting the ball was, how accurate that means your posture for yoga. Okay, so these are the very very important activities which are being planned, and researchers are trying to use this type of networks to analyze those activities. The video caption which was there is fine, but they are trying to do dense captioning. Dense captioning means it is actually trying to correlate correlate the objects in the video sequence. And this correlation also is a variation with time. If you take a sequence of images, right? Maybe there's a very beautiful benchmark video where the two men meets and then they separate out. Okay, so can you annotate that? Can you annotate those type of information, right? So these are the way how they're trying to do a spatial and temporal localization. So video captioning by spatial and temporal localization, which means that you are not only trying to understand the activity over a large number of frames, but you are trying to understand that what are the changes for each of the objects have happened, okay, in the spatio-temporal domain, right? And you are trying to find and you are trying to map those changes to specific classes, and that's what is spatio-temporal localization, where people have also tried to localize atomic visual actions. Atomic visual actions means the actions which are not gross actions, okay, which are actually very specific actions, okay. And these are very important, okay. That means and that means not disclosing at this point of time. We have a lot of discussion with one of the industry R&Ds, where they're very much interested to set up this type of applications for departmental stores, where we will not be having people to what I can say, people to help the customers. Okay, there will be more okay, visual stations and robots, might be robots, which will help the customers, and how they will know that what customers are doing. They will annotate and they will try to grab each of these spatial, and they will try to localize the spatio-temporal information, and okay, and those are the applications which are there in the future to come. Okay, so what I discussed in this lecture, okay, is that we tried to focus that okay, detection and classification of activities in video has a wide range of applications, right? Okay, I have named a few of them. Understanding the spatio-temporal information is the key factor here. How best can we do that? How accurately can we do that? And we have seen that there are a good number of deep networks which can be engaged or which can be utilized to understand or to extract the features and to categorize or to classify the video information using the spatio-temporal strategies. Obviously, we didn't discuss much on this, the performance versus processing cost, but I think getting into the complexity of the networks, what I discussed today, I think all of you will be pretty okay. That means you will be in the same page with me that these are not very easy processing architectures, right? So I think if you are thinking of the performance and the cost in terms of real-time completion of the task, cost in terms of the amount of memory resources we require, what are the different types of processing architectures can reduce these activities, I think those are the questions which I leave over to all of you, so that you can have the lot of food for thought after my lecture. Though again, having said that, we are working in this domain. We have got a good project from DRDO Avionics Avionics research domain in collaboration with IIT Hyderabad, where the role of our group will be to generate this particular models, deep network models, so that we can analyze the video and the images, and we will try to define what will be the instruction processing cycles. We will go into that level. And provided we do that, IIT Hyderabad has a fantastic facility of fabricating the hardware. So based on our instruction processing models, the hardware will be fabricated by IIT Hyderabad. And then we are looking forward to a fantastic research activity in that direction for the next few years. So thank you all. And if there are any questions, I will be fine to answer. Yeah.
Thank you, sir, to enrich us with your valuable lecture. So, sir, I'm sharing you the questions.
So am I on time, or I missed the time deadline?
No, sir, no, sir. You are on time. Okay, sir. I'm sharing you the question.
Thank you so much.
Okay.
Okay, so there is a question from Jhilam Mukherjee that can this methodology is implemented on a single 2D image like digital X-ray?
Yeah, Jhilam, thanks for the question. So basically, that means you can do a different type of fusion in the 2D image. Okay, that means you can do a sort of frequency domain information you can abstract, and you can abstract the intensity domain information, and you can fuse that, and you can generate some better abstraction. Those are some of the fusion techniques which are being done in the 2D domain. Okay, frequency level and intensity level fusion. But what I focus today is basically on the involving the time as a parameter. So involving image frames. But having said that, if you tell me that whether if I have a sequence of X-ray images, can we do this? Okay. Again, my question is that if you are trying to find out some temporal variations among the X-ray images, maybe you are trying to do some, okay, that means your object should be dynamic. That's the most important thing here. That means so there will be two things. Okay, you can also give me another hint that you are taking the X-ray of the patient at two different intervals of time. Maybe the maybe post-surgery, pre-surgery, or surgery and post-surgery. Then I think these methods can help you. These methods can tell you that that means you can then use a classifier and tell that, oh, the post-surgery recovery is good or post-surgery recovery is bad. But I think this will be a that means if you can work on this, Jhilam, it will be good that you can try to define a problem. If problem scope is there in the X-ray 2D domain, yeah, we can surely take it up. Right, and for all of you, and for all participants, Jhilam is my PhD student. So she has just submitted a thesis in medical image processing, and now she is a faculty in an institute in Kolkata. Yeah.
Oh, thank you, sir, for the information. Okay, sir. There is another question from Dr. K. Gayatri Devi. Is there any reason for choosing central pixel in two-scale convolutional model? Yes.
Yeah, this is a very good question. That means I have tried to tell a bit on that. Now let me explain it in more details. So this is based on the perception model of our eye. So ultimately, whatever outcome we are generating, right? In the many of the cases, it should be visualized by us, or the issue is that the features what we try to abstract, okay, we try to feel that it should map with our visual recognition. So that particular model tried to work on that principle. So it tried to use the principle of our capturing the visual features by our eye, which is basically done maximally by the fovea region. So what happens? You can just do a very simple experiment, right? Okay, you can. I don't know that means how you can do that, but I think there are some ways you can. If you can put a slit which blocks the central part of the eye in some way, but your side views are okay. Okay, you will see that the information what we get is basically a very blurred information, because Your fovea is a which actually tries to capture the center part of any frame, right? And that means if we try to categorize or classify a particular image, the most important part you observe is what the central part of your image. So try to think in the context of classification. You are given an image and you try to tell whether this is a dog or this is a cat. Okay, if the dog and cat is in the extreme corner or in the periphery, it will be very difficult for you. But if it is in the center, if the dog is at the center, you will tell, hey, it's a dog, or hey, it's a cat. So how you do that? You do that because the center of your eye, okay, has a maximum response. So that's the same principle has been taken here. So you take the central part of the image, you take, okay, and you take an 89 cross 89 pixel from the central of the image, right? And rest you take a downsampling of the entire image, and then you fuse the two. Okay.
So, okay, sir. So, ma'am has one more question, that
Yes.
techniques that can separate spatial and temporal information. What are the techniques?
It's a not very that means, see, if you want to segregate it as a feature space, you can just don't fuse. You just run two convolution channels, one on the spatial, one on temporal. You will get it. That if you want to do some separate activities using temporal and spatial, actually there are some networks. I didn't get into this. There are some networks which actually takes the temporal channel and then processes it using some RNN, okay, and takes the spatial channel and also tries to process it using so using some convolution network, and then they try to fuse both of them. That means you can always do that. You can always separate out the spatial and temporal channels, and the temporal channels primary features. In the spatial channel, primary features are your intensity patches. In the temporal channels, primary features are your dx and dy vectors of your optical flow. Okay? Right? And then you generate the optical flow for the next abstractions. See, so you try to. I mean, this may be pretty difficult to understand, but once you get it, it will be very. That means I think you can perceive that. So what you are doing in the spatial channel, you are trying to take an information. Take the feature space. Okay, initially from the intensity space, and then you generate the next feature space, and then you try to again work on that. In the temporal domain, you try to work with the primary, primary optical flow from the primary features in the pixel optical flow. The next level optical flow will be the edge optical flow, and this way it will work out. Okay, so that's the way you will extract the temporal features.
Okay. Hope, ma'am, you are satisfied with the answers. So there is a question from a student, Ritam. Can we reverse engineer the process of convolution? Like, can we get the original image from the detected image features?
You can do if the convolution is perfectly lossless. You can do the inverse transform, but it's not. Right? You are doing a pooling. You are doing a max pooling or average pooling, where you are losing, and also you are doing a normalization, where you are losing a lot of the information which are not contributing to your feature kernels. So it is not a lossless operation, and as it is not a lossless operation, maybe with some prior you can do it. But if you just tell me that, hey, I got the feature, the hierarchical feature vector, feature map, and try to convert it to the image back again, you will not get it, because you have done. It's a sort of abstraction. It's a sort of thing that, the student is good in science. It doesn't means that whether he has got a 98 in the chemistry or 99 in mathematics or 97 in this. That means you know that the student is good in science, and that means and he will actually go to the go to the science stream in the 10+2, or the student is good in humanities, so the student will go for humanities in the 10+2. So that's the abstraction you do. Okay.
Okay. I think Ritam, you got your answer. So there is another question from Mr. Devashish Patro. Is there any possible way to differentiate between original video and fake or tempered video using spatial temporal feature?
This is a very good question. Yeah, I also did this. I also do, that means I also don't know the answer at the present point of time. We are working on the techniques again, where we are trying to okay, trying to uh, train the generator model, okay, and try to find out how the generator model exactly copies the original information. But yeah, but yes, that means I think there might be some way, because that means if we try to compare, okay, compare the feature spaces, okay, in some way, in some plane, right, with some metric, you have to define what metric you are comparing. That's the most important part of this, right? So if you can generate a metric, and I think it will be then, as you are trying to analyze it in the two domain rigorously, spatial and temporal, right? I think you will have the differences which will be emerging between the fake and the original. But I don't have any support in terms of research and in terms of experimental data, and that's really a very good query. I will record this, and I will try to check this out. Thanks for the question.
Okay. Thank you. Sir, one more question. This is from Professor Rajkumar, R. Rajkumar, that whether MATLAB is better or any other software is better for machine learning.
See, I cannot directly tell any software is good or bad, in the sense that because we got a lot of support from all the software vendors, right? In the right way to say. It is not that. But I personally is a strong believer of open source, especially in academia. In the industry also, people will differ in industry. If there are any experts from industry here, they might differ. There is a difference in opinion in many of the cases that the open source software doesn't gives you the same amount of quality with the labor what you give. It might be true in many of the cases, but I still believe that if you are working in academia, okay, we have a lot of constrained environment, our funds and our things happens. If we have some open versions which works, okay, I think a lot of open version tools, okay, in the Python platform, you can check, and I think they can an OpenCV, OpenGL, these are CUDA, these are all the platforms what you can try for your activity. But having said so, that means I am not in opinion that any tool is that established. All the established tools are good. All the established tools, okay, it helps us. But in academic setting, we have found, due to our fund, due to our resources, that okay, and presently we are using heavily the cloud platform. So we know that in the cloud platform, in the Google Colab and all these platforms, they give you the Python flexibility of Python, and you can share the Jupyter notebook with your groups. So these are all the things what you can do in the open source platform.
Okay. Thank you, sir. So, from our college, Lipika ma'am have some question. Ma'am, are
Sure.
you there? Lipika ma'am. Uh, I so
If Ripika ma'am is not there at this point of time, we will gather the question from her and we will
Yes,
share it with Professor
yes,
Chakrabarti later on.
yes. You can mail me.
oh,
I will try to do my best to answer that.
okay. Thank you, sir. Now I request our HOD ma'am, Dr. Shabnam Sengupta, to uh, continue the token of appreciation on behalf of the organizing team. Ma'am, please.
Thank you, Professor Chakrabarti, for the wonderful session. And I'm sure that many of the participants will be immensely benefited and immensely motivated to pursue research on this particular domain. And I also like to mention that we have a fantastic audience because we got lots of questions and most of them are very relevant. So I must congratulate the participants as well for being such responsive participants. So this is just a small token of appreciation from us, from on behalf of the Department of Information Technology for this
Thank you,
wonderful
Professor
session.
Shengupta, and thanks to the department for offering me this very beautiful token of appreciation. Thank you.
Thank you, Mr. Chakraborty, and we hope that soon we will meet and we
True.
will be able to organize these kind of sessions as physical seminars and workshops and conferences. So let's hope for the day.
Thank you.
Thank you, sir. Thank you so much, sir.
Thank you, Dr. Chakraborty,
Thank you,
for the
Principal Ma'am.
session.
Thank you. We hope that we will meet after the pandemic ends,
Yeah, sure,
and we
sure. We are
want it
looking
as
forward.
at
All
the
of us.
earliest. We all hope
Yes.
that the pandemic ends up at the earliest.
Exactly. Exactly.
Thank you all.
Please
Thank
stay
you so
safe.
much, sir.
Everyone, please stay safe.
We will
Uh,
have our day two session tomorrow. So, Shripta just announced about the
yes,
feedback link. No?
yes. Thank you, everyone. Now, regarding the feedback link, it is shared in the Facebook as well as in the Gmail, and also it will be shared in the WhatsApp group. So please fill up the feedback link. It will be available till 7 o'clock.
I think
Oh,
it's
so already
already
the
done.
time. Oh, so means half an hour. It's will be there, I guess, up to 7:30.
Yeah, so Dr. Shutapa, also you can forward my email to all the participants if they have any questions after that, after their and also I will forward this PPT
That will be
to you.
wonderful.
That means you can circulate this if they come across any queries after this, I will be very happy to answer those. Okay.
Sure, sure,
Yeah.
sure.
Thank you all. So
Thank
I
you,
am
sir.
taking a
Thank you
leave.
Thank
for
you,
your
sir.
contribution. Thank
Thank
I'm
you,
you,
sir.
taking
sir.
a leave from all of
Thank
you.
you,
Thank
sir.
Okay.
you.
Thank
Thank
you.
you,
Thank you.
sir.
Thank you, all of you. And we are really privileged that we have participants from the reputed international and national institutes. So thank you all of the participants for your gracious presence. Thank you once again. Thank you. Let's meet tomorrow in the next day, our series, tomorrow's session. Thank you, everyone.